Welcome to the part 2 of the lecture tutorial for the tutorial number 5, Interference, Applied Physics, course code UPH004. So in this part 2, we'll be solving the question number 5, 6, and 7, and 8. To start with the question number 5, here the problem description is like this. A thin film of MgF2 magnesium fluoride is deposited on a glass so that it is anti-reflecting at a wavelength of 580 nanometer under normal incidence. What wavelength is minimally reflected when the light is incident at 45 degrees? To understand the question number 5, let's first draw a diagram of the situation. So here a thin film of magnesium fluoride is deposited over a glass. So here is our glass, and then on top of it there is a thin film of, this is glass, and the refractive index of the magnesium fluoride is, when the light falls normally onto this surface, then this magnesium fluoride surface becomes anti-reflecting. So what do I mean by anti-reflecting? The light falls on the surface, then the surface do not reflect any light. Everything gets absorbed or everything gets transmitted. So no light is reflected. So that is anti-reflecting. To make this surface MgF2 anti-reflecting, that all the reflected light from this thin film making a destructive interference on the surface here. If that is the case, then no light would come out of this surface. So the situation is, for material to become anti-reflecting, the interference of the reflected light from the thin film of magnesium fluoride must interfere destructively. The condition for the destructive interference is where n is the order of the interference. This is for destructive interference. So generally you will find for that reflected ray, the minima condition is n lambda, but here I have written 2n plus 1 lambda by 2. Why is that? To understand, what you have to be mindful of is that here this is air, then this is magnesium fluoride, then this part here, this is glass. So in all cases, as the light enters from air, comes into magnesium fluoride, then light is going from a rarer medium to a denser medium. Then again, when the light goes from the magnesium fluoride to the glass, then again the light is traveling from a rarer medium to a denser medium. Now in that case, the light that gets reflected from this surface like this is getting reflected from a denser surface. Similarly, the light that is getting reflected from the glass surface coming from the magnesium fluoride surface is also getting reflected from a denser medium. That's why the phase difference between this ray here, this ray, and this ray is 0. They are both having the same phase, and that's why the condition gets reversed, and now the is equal to 2n plus 1 lambda by 2 here. Okay, so you have to be reminded of this situation here. For this magnesium fluoride thin film to become anti-reflecting, what you have to have is the minimum thickness of this thin film. The n should be minimum, so n should be is equal to 0. So in that case, the thickness is, and this turns out to be is equal to, so this is equal to, finally, for the second part, what wavelength is minimally reflected when the light is incident at 45 degrees? We have to find out wavelength. Lambda is equal to how much? This is equal to, now to find out the value of the cos r, we have to work a little bit. So you have to use Snell's law. That implies, so this would give ultimately cos r is equal to, so the final result, lambda is equal to, so this is the wavelength of the light that gets minimally reflected from a magnesium fluoride surface having thickness 105 nanometer over a glass surface when the incident angle is 45 degrees. So in the question number 6, what we have is, if the diameter of 10th and 15th dark rings of a Newton ring pattern are found to be 6 millimeter and 8 millimeter respectively, find the diameter of the 5th dark ring. Plain glass plate and plano-convex lens combinations is used to produce interference pattern due to reflected beams. In the Newton ring experiment, the wavelength is calculated using this formula, where dn and the lambda is the wavelength of the light used for observing the Newton ring pattern. Now given, we have to find d5. Now we can use the formula for the lambda. This would imply r gets cancelled out, 4, 5 all gets cancelled out. Ultimately, we'll rearrange and solve for d5. So this ends our problem number 6. Now the question number 7 reads, Newton's rings are formed in the air film enclosed between a plano-convex lens and a plain glass plate by reflection. Diameters of 4th and 20th bright rings are respectively 0.203 centimeter and 0.484 centimeter. Show that the lens and the plate are not exactly in contact. Also find the wavelength of the light used. Given data are radius of curvature of the plano-convex lens is 50 centimeter. Diameter of the 4th bright ring and expression for nth bright ring is, for such a plano-convex lens Newton's ring setup, the central ring must be equal to a dark ring. So the Newton's ring would look like this, with the center dark, then a bright, then dark, then a bright, then a dark, then bright, and so forth. So here for the bright, n is equal to 1, then n is equal to 2, n is equal to 3, n is equal to 4. For bright fringe, 4th ring has n is equal to 3. So first ring, second ring, third ring, fourth ring, 20th ring. Hence what we have is from here lambda for the fourth ring must be equal to, this is equal to, and similarly for lambda is equal to 20. So what happened here is the wavelength as calculated using the diameter of the fourth ring and the diameter of the 20th ring turns out to be different, though which is not the case for the Newton's ring. In the Newton's ring we used the same light, we didn't change the wavelength. It's just one simple monochromatic light. So in this case the lambda must have been same, but it is not. In one case it is 589 nanometer, another case 601 nanometer. So what this implies is either the rings were miscalculated or there was some gap between the planar convex lens and the plate, and that's why there is a discrepancy in the wavelength as calculated from the given diameter of the ring, 4th and 20th ring. So in short, the diameter of the rings are not reliable, or there was a gap between the planar convex lens and the glass plate. In the second part of the problem, it asks to find out the wavelength of the light used. The wavelength of the light used is to be found out using this formula. Here, because we are taking the differences of the diameters, that's why whatever error in counting the rings that we have made in case of D20 or D40, that gets cancelled out in this formula. So our final result is lambda is equal to 603 nanometer. So that ends our question number 7. The question number 8 reads, the diameter of the mth dark ring in Newton's ring experiment changes from 3 mm to 2.5 mm when the air film is replaced by a liquid. Find the refractive index of the liquid. So we have this Newton's ring setup. The question is that when we replace this air film with some other liquid, then the diameter of the mth dark ring, 3 mm for air and 2.5 liquid, some other liquid. We have to find out the refractive index of this liquid. To do this, use just one simple formula. We have dark ring diameter is given by when the film is of air. This is for air film. But for any other liquid, the formula is with liquid, where this mu is the refractive index of this liquid. We can take the ratio of these two expressions, and what we'll have is that mu is equal to square. So here these are all squared is equal to, so our final result is the refractive index of the liquid is 1.44. So that ends our last problem. And again, thank you very much for sticking up to this. Thanks.